hunting ghosts in the sky and finding what makes their colors. Scientists captured new imagery of atmospheric phenomena that occur during some lightning storms, offering clues into how they form. In June 2019, scientists in Spain went searching for ghosts haunting the skies above the Mediterranean Sea. These green-hued wisps, dancing above pink-red, extremely high-altitude lightning during thunderstorms, had been discovered only in May that year. What were they? The only way to know was to capture one. But that would prove to be a troublesome task. These ghosts are aptly named. They are difficult to see with the naked eye and appear for just a heartbeat dozens of miles above ground. Seeing a ghost is really difficult, said Maria Paces Vero, a researcher at the Institute of Astrophysics of Andalusia in Spain. But on September 21, 2019, they finally caught one with a specialized camera, a green spirit flickering at the crown of a jellyfish-shaped maelstrom of fuchsia lightning 50 miles above the sea. And after painstakingly disentangling the various wavelengths of light emitted by the ghost, the scientists unveiled its elemental makeup. In a study published Tuesday in the journal Nature Communications, Drive, Paces Vero and her colleagues revealed that the ghost's pale emerald complexion came, in part, from excited oxygen, similar to the green glow of auroras. Nitrogen plays a role, too. But the main contributor was another element, iron. That was a surprise because the metal was ultimately being delivered from space. Better understanding ghosts and other ephemeral lightning-like entities can help scientists interpret the difficult-to-parse chemistry and physics of Earth's upper atmosphere. There are layers of metals that dance, in and above thunderstorms. Drive, Paces Vero said. Ghosts are a type of transient luminous event, or TLE, which were first described by scientists in 1989. TLEs can include blue jets, which fire upward from thunderstorm clouds, as well as crimson-tinged upper atmospheric lightning that can come in many shapes, like carrots and jellyfish, and is known as a sprite. TLEs are like fireworks. Drive, Paces Vero said, and little is definitively known about them, especially ghosts, the first of which was observed atop a sprite storm over Oklahoma in May 2019. To capture their own ghost, her team pointed a spectrographic camera, one that can use light to ascertain chemistry, at the upper atmosphere from an observation post in Castellgalí, Spain. All they could do was wait for sprite thunderstorms to appear, cross their fingers and hope that at least one sprite would be briefly decorated with a ghost, and that their camera was pointed at the right place. Eventually, they found one flitting about on a jellyfish sprite. It was a matter of luck. Drive, Paces Vero said. This one was largely powered by extraterrestrial iron, not atmospheric oxygen. The camera also revealed the presence of nickel, sodium and silicon. The complex chemical soup responsible for this ghost even added a yellow-orange tinge to its green glow. All of those elements often come from micrometeoroids and deep space dust particles that are nearly constantly plunging into the upper atmosphere. That means that ghosts could effectively be seen as interplanetary visitors. Still, some researchers said not too many conclusions should be drawn from the new paper's findings. The metallic traces are interesting, but I'll caution that this was only a single event, said Chris Vygotsky, a lightning researcher at the University of Wisconsin-Madison who was not involved in the new work. To see if all ghosts are iron-fueled spooks, he added, it would be nice to see the results from multiple ghosts. He has no doubt that the search for ghosts, and other TLEs, will continue, largely because these phantoms are inherently beguiling. It's really incredible to think that there is so much more occurring during a thunderstorm than what you can see or hear, Mr. Vygotsky said. Spectroscopy of a mesospheric ghost reveals iron emissions. Mesospheric green emissions from excited oxygen in sprite tops ghosts are infrequent and faint greenish transient luminous events that remain for hundreds of milliseconds on top of certain energetic sprites. The main hypothesis to explain this glow persistence is the long lifetime of excited atomic oxygen at 557.73 nanometers, a well-known emission line in aurora and airglow. However, due to the lack of spectroscopic campaigns to analyze such events to date, the species involved in the process can not yet be identified. Here we report observational results showing the temporal evolution of a ghost spectrum between 500 nanometers and 600 nanometers. Besides weak but certain traces of excited atomic oxygen, our results show four main contributors related to the slow decay of the glow: atomic iron and nickel, molecular nitrogen and ionic molecular oxygen. Additionally, we are able to identify traces of atomic sodium and ionic silicon, these observations being consistent with previous direct measurements of density profiles of meteoric metals in the mesosphere and lower thermosphere. This finding calls for an upgrade of current air plasma kinetic understanding under the influence of transient luminous events. Transient luminous events (TLEs) are huge and brief optical and electrical phenomena occurring over thunderstorms, in the upper regions of the Earth's atmosphere, after high-energetic lightning activity. They are also known as upper atmospheric lightning, and the most common TLEs include sprites 1, halos 2, elves 3, blue jets 4, and gigantic jets 5. TLEs were serendipitously observed for the first time in 19896 and, since then, sky photographers all around the globe spend the nights chasing and sharing these breathtaking flashes of light. It was May 2019 when, while documenting a sprite storm over Oklahoma, a citizen scientist realized that a greenish glow appeared on top of certain energetic sprites and lasted for several milliseconds. 7. This new phenomenon was named then from the acronym of green emissions from excited oxygen in sprite tops GHOST because, up to now, the main hypothesis to explain its greenish color is the excited atomic oxygen at 557.73 nanometers 8, 9, a well-known emission line in aurora and airglow 10. Since the uploading of this finding to YouTube 11, the TLEs community started to pay attention to these rare greenish emissions 8. In June 2019, we initiated a systematic spectroscopic campaign aiming to understand the chemistry and dynamics related to ghosts. The objective was to analyze the temporal evolution of the spectral emissions occurring on top of sprites, in a wavelength range from 500 to 600 nanometers. In this paper, we show the spectrum of a mesospheric ghost and its temporal evolution. Although the results confirm weak traces of excited atomic oxygen (OI) at 557.57 nanometers, we are able to identify four main species associated with the gradual fading of the ghost brightness: atomic iron Fe, nickel Ni, and nitrogen Ni, molecular nitrogen N2, and ionic molecular oxygen O_2 Besides, our results show traces of atomic sodium, Na, and ionic silicon, C2. This finding would require an upgrade of current air plasma kinetic models to predict the optical emissions of TLEs 12, 13, 14, 15 because, so far, there is an absence of metallic species in their implementation. Results: imaging and lightning activity. The spectra we report here were observed with an upgraded version of the Granada Sprite spectrograph and polarimeter GRASSP 16, 17, 18, 19. This intensified slit spectrograph is located at 41.677 ring operator N, 1.840 ring operator E, elevation 276 meters above the sea level, in Castellgalí, Barcelona province, Spain. Since June 2019 we have recorded the images and spectra of 42 sprites with the spectrograph slit projection overlapping their top diffuse region, where mesospheric ghosts are likely to appear. From these 42 events, only one showed a spectrum brightness with a significant signal-to-noise ratio. The event we refer to occurred on the 21st of September 2019 on top of a jellyfish sprite that emerged from a thunderstorm cell developed over the Mediterranean Sea, at approximately 370 kilometers distance and 84.1 degrees azimuth from the observation site, as Fig. 1 shows. The Lightning Detection Network (LINET) 20 detected the 178.2 kA peak current cloud-to-ground parent stroke, 41.9324 ring operator N 6.2828 ring operator E, at 19 hours 44 minutes and 30 seconds. 514 UTC. Table 1 shows LINET lightning activity on the 21st of September 2019 from 19 hours 44 minutes and 29 seconds. 765 UTC to 19 hours 44 minutes and 32 seconds. 123 UTC within the area of interest. A video camera with a 720 nm infrared pass filter was used in time-lapse mode at 1-second intervals to capture high-resolution images of sprites and the hydroxyl O airglow background. In these images, we identified a thin cirrus cloud band across part of the sprite, which did not affect the region where the spectra were taken. Panel of Fig. 2. The banded structure visible in the upper part of both panels of Fig. 2 shows a slight curvature consistent with concentric gravity waves propagating away from the convective core of the thunderstorm system that produced the sprites 21, 22, 23. Panel B of Fig. 2 shows the composite image of the reported event. We estimated the dimensions of the sprite as approximately 47 kilometers height and 60 kilometers width, and the altitude of the slit projection around 82.8 plus or minus 0.4 kilometers, according to the star fitting method 24. Unfortunately, the infrared long pass filter at 720 nanometers and the 1s exposure time of the imaging camera prevented us from detecting the ghost in the frames before and after the sprite. However, the intensified spectrograph camera showed an increase of the brightness in the spectral range between 500 and 600 nanometers before, during and after the sprite, implying a previous slow enhancement and further decay of green emissions from the top of the sprite. Line identification. We analyzed 45 consecutive spectra of the reported event, from -480 milliseconds to 1280 ms. Being t equals 0 ms the time coincident with the sprite. We detected a global enhancement of the spectral brightness starting approximately 200 milliseconds before the occurrence of the sprite and continuing for 480 milliseconds thereafter. We observed 2 distinct stages of this brightness enhancement. In Table 2, Set A, the identified emission lines, see methods subsection line identification, enhance their brightness level during the initial stage, from -200 milliseconds to 120 ms. Meanwhile, in Table 3, Set B, the emission lines showed an enhancement in their brightness level from 120 to 480 milliseconds, corresponding to the secondary stage. We identified the OI, 557.73 nanometers, FAI, 522.06 nanometers, 529.07, 535.63 nanometers, 538.22 nanometers, 563.96 nanometers, 580.45 nanometers, 583.46 nanometers and 586.72 nanometers forbidden atomic emission lines, and the N2 Vagard-Kaplan (VK) molecular emission band. Line flux. We calculated the line flux, see methods subsection line flux, evolution of the identified species in Tables 2 and 3. Right axis of Fig. 4 shows the temporal evolution, from -480 to 1280 ms, of the normalized average of the line fluxes of the identified species in combined Set A and Set B, black solid line. Previous imaging research on mesospheric ghosts reports green emissions to follow similar behavior. 8. A gradual enhancement reaching its maximum coincident with the sprite occurrence, followed by a further and abrupt decay and a final increase leading to subsequent stabilization. If we focus on the identified species at the initial stage, Set A, we observe an increase in their average line flux, dotted black line, right axis of Fig. 4, from 200 milliseconds before the event occurrence, reaching its maximum level, and then abruptly decaying until 120 milliseconds afterwards, when it stabilizes. On the other hand, we observe a gradual increase in the average line flux of the detected species during the secondary stage, set B, from 200 milliseconds before the event occurrence to continue up to 320 milliseconds afterwards, reaching its maximum level. Subsequently, it smoothly decays until 480 milliseconds, at which point it stabilizes.